Um, Hello, everybody. Is my screen visible to you?
Yep.
Okay, okay, cool. So let's get started with our first tutorial. So this tutorial is just a demonstration of how to use ScaleSim as a package. So if you guys have access to your web browser, right? I would encourage you to download the tutorial files from here. So it would be nice and interactive. Otherwise, like no worries, you can stick around and then I will also run the tutorial on my screen and you can see it. So, so for the first part, what we are going to do is to show how to get quickly started with ScaleSim, and I will be using Google Colab for it. So if you download this file, right, you will see a file like this. One second. So you will see a ScaleSim bundle kind of file like that, and then we have a file called tutorial code.txt. In tutorial code.txt, you can go through this, IPython notebook, which basically will take you here. And then you can open it in Google Colab and we just run this file as is. So what we are going to do is I wanted to show you how to set up using a simple pip command. Then how do we prepare the inputs, and then finally launching the simulations. So setting up ScaleSim is really easy, and the only command which we need is pip install ScaleSim. So if you have it, if you have your Google Colab open, so let me make it a little bit more. Or just let me know if it is not visible clearly. I will make the sizes larger.
You could probably get a little bit larger, Anand. Yeah, that's
Okay.
Good for me. Yeah.
Okay, cool. All right. Thanks, Paul. So so installing ScaleSim is really simple. So here we have this command, which is pip install ScaleSim. It downloads the latest PyPI package and it installs in your machine. So let me just do run anyway. And that's it. So we have it installed. Now in my Google Drive, I have the path to the config and topology file here. So let me just quickly show you what it is. So quickly connect to Google Drive, and okay, so in my drive, I have ScaleSim resources, and these are the config which we were using. So this configuration file basically tells me that yeah, this let me just show you from here. Yeah, so this configuration file basically tells me that I'm using a 32 cross 32 array with 64 KB of SRAMs for each of the buffers, and I'm using I will be running in user bandwidth mode with a bandwidth of 10 words per cycle in wait stationary data flow. So once we do that and link the files here, so we do from ScaleSim import ScaleSim, which is just importing the package, and we gave the file paths over here. Then we just instantiate a simulator object, and finally we just run ScaleSim using this command that run scale top is equal to this whatever path we want our test run results to be in. So if I just run this over here, it imports the package. If I do this, it instantiates the object of the simulator, and then finally, if I run it, you can see that it's generating the output. So it takes I mean, depending upon your computer, it takes from a few seconds to a few minutes. So here it looks like it's going to take about a minute. So while it runs, let me just quickly tell you that what outputs we are expecting. So this is quite similar to what I have talked in my previous presentation. Oh, by the way, is this recording, or do you guys know? Oh yeah, it's recording. Sorry. Yeah, so it gives us total runtime and stalls. and then it gives us the array utilization and the overall the mapping efficiency and the overall utilization, and it will give us the interface bandwidth, and finally it will save the traces. So let me just wait for this to complete. So for a few 10 more seconds to go. And that's about it. So now it is saving traces, but the run has finished. So it is that simple to set up. So so before running this tutorial, right, I just had these files in my, you can say, the file explorer, and ScaleSim was not installed. And I think it just took us like 10 minutes to do this entire PPT plus actually installing the tool and running the tool itself. Yeah, so with this, I wanted to give a quick demo for setting up ScaleSim for design space exploration. So there are two parts in this demo. So first part is just showing that, how should I pick a data flow using ScaleSim if I don't want to do any mapping exploration beforehand. And then second, I will show that how the array microarchitecture, along with the mapping, kind of affects performance and how you can choose that using ScaleSim. So before I start that, does anybody have any questions?
I have a quick question. I can see there are multiple config files, one like for Iris, Chip, and the Google one. So I'm wondering, like, does those like validate against the published result by Google and Iris?
So actually no, but we did run the TPU once, right? So the Google one is just the TPU parameters here, and then ScaleSim, like I said, for our ASPLOS submission, we did validate it against an RTL design. For Iris, actually, Iris is not a systolic array per se, but this is basically a systolic array equivalent of the Iris configuration. So you will have a little bit difference between the performances. And also, I mean, we do not have very fine-grained details about these accelerators. So it is a best effort kind of thing to get as close to the performance or the configuration space of Iris and Google are concerned.
Thank you.
Okay, so let's go into the next tutorial. So again, if you have downloaded the files, right? So you will find another link over here, which is for part B. And if you click that, it will take you to this particular Google Colab. So let me just make this a little bit larger. So before I run this, let me talk about a little bit. Let me give you a little bit prelude. So the hardware parameters that we are using in this particular run is a 64 cross 64 array with 500 KB SRAM sizes, and it is again, what we will do is we will use this kind of this kind of a configuration file with only the data flow changing when we are searching. So there are essentially 3 files which I'm using, and these 3 files have only only difference is the data flow which changes among them. And the input workload which we will be using for this tutorial, it looks something like this. So it has one 3 cross 3 convolution, one 1 cross 1 convolution, and one fully connected layer, which is like really large. So it will result in a 2048 cross 1000 matrix. So with that, what we will do in this tutorial is first install and initialize the tool like we did in the previous one, run the simulations, and then analyze the outputs. So so obviously the first step is to install ScaleSim again. So if you are following along with the text file, so what you can easily do is just copy and paste. So the install part is already there, but for the next portions, you can just go ahead and copy and paste code from here. So after this, after we install it, obviously we are importing scale sim library. So first, this is a simulator, and then we have a small reporter to pass the outputs. And we are using NumPy and Matplotlib to plot and do some manipulations in this tutorial. So next, we will just do one run for the output stationary configuration. And to run that, if you are running along with me, just to copy this snippet over here, which is under this code for run scale sim method, and just paste it here. And if you do that, so this defines run scale sim. Okay, so let me just run from the top. Okay, so then import libraries, import scale sim, set the paths, define this guy, and then yes. So let's define run scale sim. And then finally, once we have defined it, let me just run this method using this run scale sim call. Oops, something happened. Okay, so I did not link my Google Drive. Okay, now it should work. Okay, so it now started running, and you will see that in contrast to what we have run before, it is now working in an estimate bandwidth mode. So it will give us that how much bandwidth we need in the interfaces to have zero stalls. So let it run for a while. All right, so it has run the first layer and it shows that we have 99% mapping efficiency in output stationary and for the first layer, and we have 81% of overall utilization. And for inputs, we are good with about 10 words per cycle. For output, it is pushing out at 64 words per cycle, which is basically streaming the outputs out. And in this case, we have 100% mapping utilization, but because of mismatch in layer dimensions or the pipelining delay, sorry, the overall utilization is kind of low. And then finally, it will run for the third layer. And then we have the data for all the layers. So I actually pre-run these things for the two other wait stationary and input stationary data flows. So I'm just going to call a method to to just read those the outputs of these runs and then plot them. So I will just explain this method briefly over here. So what we are doing in this is basically loading the data using a utility inside ScaleSim. And once we load the data, we just get the compute cycles for all the layers for output stationary, wait stationary, and input stationary. And finally, we go ahead and plot the data. So let me do the same thing in the Colab notebook. If you are running this, then what you can do is just copy and paste the code from here. And so this is there. And then let me just quickly go ahead and call this function. Okay, so once we, so what it did is it went ahead and read the data initially, and then it shows that what are the run times for different layers. So there were 3 layers, like I said before. So what the run times were, and clearly we can see that the output stationary one won, because not because that it is best for every layer, but it is reasonable for each layer. So the overall runtime is low. You can see in the wait stationary that it did really well for the first 2 layers, but it did not quite work for the last layer, which is why it could not outperform output stationary. And similar is the case for input stationary. So it really, the data flow choice really does depend upon what kind of layers you have. For instance, if we only had the first two layers in our network, then the weight stationary implementation would have been the winner. So this was a simple example, so it was pretty straightforward and intuitive to reason about it. But it becomes really, really tricky when you have large networks and when you have a collection of networks and you wanted to zero down onto a mapping strategy and array dimension to before you begin writing your RTL or taping out your accelerator. So this tool can like help you get those insights pretty quickly. So I think that covers what I had to talk in this particular slide. So let's move to the next part B of the demo. So I'm going through this demo pretty quickly, but if you have any questions in between, just feel free to talk. We have enough time, I think, to answer all your queries. Yeah, so does anybody have any question now before I proceed? Okay, so if that's the case, then let me talk about the next part of the demo. So what we will do in this case is in addition to changing the data flows, we will also change the aspect ratio of the array while keeping the number of MAC units constant. So you know that we use 64 cross 64 array, and with the same amount of MAC unit, we could have constructed 32 cross 128 or 128 cross 32 or something like 4 cross 1024 or something in between, and then run all the three data flows on them, and then figured out that, oh, for this particular network, which configuration kind of made most sense. So in this exercise, we will deal with about 27 configurations. So it's going to be pretty interesting. So the configuration, what we are going to do is, this is the new function which we are going to add. So because the runs take a little bit long time, I thought that it would be a good idea to just run them beforehand and read the data like we did in the previous one. So that's what I'm going to do. So let me just quickly copy and paste the code for this. And what this code essentially does is very simple, right? So we have the three layers over here, and it searches through the different rows and columns. So obviously, since the number of max is restricted to 2 raised to the power 12, so if you fix the number of rows, you can automatically calculate the number of columns. And then for each of these rows and columns, it iterates through a data flow. And then, I mean, I ran all of those simulations, but in this case, I'm just reading the report generated by those simulations and creating a table which is later passed on to this plotting method, which plots them as a stack bar. So let me just do that. So here, so I can just to compare. Oh, I think I did not run this. That's why it is giving me. Yes. So if I do that and run it, so right now it is reading all the different files, as you can see over here. Yeah. So we have this plot generated over here. So this plot actually is pretty interesting, right? So the reason is, initially we have this familiar U shape over here, but the best configuration is 16 cross 256 output stationary, which which is a skewed array. So it's probably very interesting to know that the traditional square array kind of shape, although they did good, it was not the best. Like we can do better if we go and look at the aspect ratios. And like data flow, the choice of aspect ratio is also workload dependent, right? So for instance, if we had only first two layers, probably something else, I'm guessing this 64 cross 64 weight stationary would have won. But right now, because of the presence of the last layer, this short but long kind of a array with output stationary data flow one in this particular case. So anyways, I mean, I did not intend to go ahead and analyze this artificial topology in detail. I just wanted to give you an idea that these kind of analysis is really, I mean, this is a bread and butter if you are designing a DNN accelerator, and ScaleSim kind of lets you do it right out of the box. You don't even have to go ahead and change anything in the code to do to perform this kind of design space exploration. So that actually brings me to the end of this presentation. So we have next presentation from 12 o'clock. So I think we have 10 more minutes for questions, and then we will take a 10-minute break. So yeah, feel free to ask any questions if you have here.
Question, and which is more general than using the tool. So I was wondering, like, so you said like there is like you need to do some kind of transformation for the input feature map before you run it systolic array, right? So I was wondering if that transformation also take into account the cycle counts need for that transformation, or you assume that the data is already transformed into the right format before you do the computation.
So I'm sorry, I lost the audio in between. But if I understood you correctly, you are talking about that between layers, the data transformation needs to happen, and whether or not that is taken care of, right?
Sorry, I guess it's my connection. So I asked the question again. Can you hear me now? Hello? I probably put the question in the chat box then.
Anand, I'm afraid your audio is broken.
Yeah, I can't hear you, Anand.
Yeah, neither do I. So yeah, just post a question in the chat box and I'll try to contact Anand on another channel.
Okay, sure.
Thanks.
Hello. Sorry, I think this is from my audio connection. So can you repeat the question once more?
Anand, I think your audio is still quite buggy. It sounds like you're underwater.
Okay, so give me one moment. Let me change my headset.
Yeah, sure. Now you're muted again, or we can't hear you at least.
Very interesting.
Now it's better, I think. Can you say something?
Can you hear me now?
Yeah, now it's working. Perfect.
Okay, sorry about that, guys. I think it was from my side. Can you repeat the question, please?
Sure. So my question was, do you take into account the cycles that need to transform the input feature map to the format that you require before you start the systolic computation, the matrix multiplication, or you assume that the data is already in the right format before you actually start the computation?
Oh, that's a good question. So interestingly, if your native operation is a convolution, right, then you don't have to take. I mean, from my experience, of course, that we don't have to take into account the transformation. So what happens is that the controller in your hardware would actually determine the matrix, the address corresponding to your unfolded or untransformed matrix when it is running. So for instance, let's say I want the second element of the first convolution, right? So I'm not sure if I'm doing this correctly, but let's say you are doing this convolution and then the filter is at the very top left corner. And then you want to know all the input elements, the addresses of all the input elements in an untransformed matrix. That can be done in, I mean, you can just run an analytical equation and figure that out. You don't have to do an into call separately and then store it again into a buffer and then run the convolution. So, so that is what I meant when I said that the native operation that we assume in ScaleSim is convolution.
So basically, the controller calculates whatever address that need to be fetched, and then it just fetch that data, right?
Correctly, yeah, correct. That's absolutely correct.
Thank you.
You're welcome. Any other questions? Okay, so if we don't have any questions, right, let's break for some time. So this was planned to be a 10-minute break, but we can add 5 more minutes and we will reconvene at 12 o'clock with Moritz's tutorial on modifying ScaleSim to add custom feature. So see you in a bit, guys.